Okay, so we're going to keep looking ahead in chapter 16, and we're coming across 16.4, which introduces the first big theorem of line integrals, and that's called Green's theorem. So for this section, I'll use a bunch of different shades of green to stay in character. And so I think the best way to understand why Green's theorem exists and what its importance is really by looking at a kind of introductory example that highlights a situation in which this theorem would be useful to use. So in this case, let's suppose that we have to compute a line integral through a vector field, which we've been doing a lot of. We've been doing a lot of these line integrals through vector fields over a curve defined by C. So here we were given a certain vector field we're looking at, and then we were given this graph that kind of displays what C is. So normally when we find the line integrals of vector fields over a path, right, the interpretation of that is the circulation. We talked about that. So if I wanted to find the circulation of f, right, of f on C, that's equal to the line integral over that path, right? But in this case, it's not possible to parameterize this path C in terms of one parametric equation, right? This would have to be broken up into two different ones. So we would actually have to write the sum of two different line integrals. So we'd have to do the line integral over C1 plus the line integral over C2. Let me pick a different contrasting color. Let's do this. So the line integral over C2, where C1 is this section, right, so from the origin along this path here, so that's C1, and then C2 would be this part of the curve. So here's C2. And if we were to write this in terms of two separate line integrals, where we would parameterize the first curve like R1 in terms of t, right? And so in this case, it's just the equation y equals x squared, which we can parameterize as x just being equal to t, and therefore y would be t squared. So we could write this as a parametric curve in the form t in the I direction plus t squared in the j direction. So that would be the r of t we would put in here, right? So that would be the one we would use for our first line integral, and then for the second one, right, the second sum, we would have, or the second term, we would have to do a second parametric equation. And this one was almost just the opposite. In this case, we could parameterize x as being t squared, and y would be t. All right, so we would have t squared in the I direction plus t in the j direction, right? And of course, both of these would have to have bounds on t, so this would have to be t from something to something, from a to b, and t would also similarly have to be bound between two values. But this is, I'm not going to solve it out because this is just an example. So in this case, with the tools we have so far, it would have to be written as the sum of two different line integrals. So this is where we get Green's theorem. So Green's theorem looks like this. So here's the full-fledged version of Green's theorem. And what it's saying is this is saying the line integral of a vector field over a curve C, right? That's what this left-hand side is, a line integral of a vector field, right, in the form, right, big F is equal to m I in the I direction plus in the j direction, right? So that's where you get m and n, those are the components of the vector field, over C, right, where C is your path you're integrating through, right? And we call this the circulation, right? And we've talked about that before. And so what Green's theorem is this is really a relationship between a line integral, and let's look at the right-hand side. the right-hand side is actually a double integral over an area, right? So this is a double integral over a region R. Let me pick a different flavor for this side, right? So a double integral over a region R of some term dx dy. So this is the relationship between a line integral of a vector field and a double integral over a region. So that's what Green's theorem is. It's this special relationship that exists between a line integral through a vector field over a curve C and how it relates to a double integral over an area in the same vector field. Now, the part that you're integrating on the right-hand side, this integrand, is what's called the curl of f. Right, so this term right here, this is called the curl of f, right? And it's a value, it's a way to quantify the microscopic circulation, right? So we talked about circulation is the tendency for a vector field to kind of cause rotational motion, to rotate a particle in the vector field. And the curl is like the microscopic version of that. So it's circulation per unit area, where the unit area gets infinitely small. So we would call this like the microscopic circulation of f, right? And so basically the curl of a vector field is the tendency for it to cause rotational motion. So, or the tendency to cause rotational motion. So the term, the partial derivative of the n component of f with respect to x minus the partial derivative of the m component of f with respect to y, that gives you the curl of f. So the line integral of f over a certain curve is equal to the double integral of the curl of f over the region R, where the region is the interior of the shape that's formed by your curve C. So in this case, the region R, that we'll be using, if we were to employ Green's theorem, the area that these two curves enclose, this would be R that we would use, right? And we know how to write the bounds of a double integral that would capture that region R. Okay. So basically, anytime you have a line integral that you would need to break up into multiple parts, you can use Green's theorem to simplify it into a single double integral. And we've been doing double integrals all the way since chapter 15. So it kind of makes it a lot easier and draws upon things that we have a lot more practice doing. So here are the conditions to apply and use Green's theorem. So a couple things must be met. So you must be evaluating a line integral over a vector field, right? That is just the left-hand side of the equation, right? So the left-hand side of the theorem is stating that it must be a line integral through a vector field. The path of integration, right, that's C must be simply connected. And you know that that's true and implied in the formula because on that left-hand side, whenever we see this circle over the integral symbol, right, that automatically indicates that the curve C that you're integrating over must be a simply connected curve that forms a closed loop and doesn't cross over itself. Now, the reason why that's important is it must be simply connected because that's the only way to capture a region that you can write like the equivalent double integral over a region, right? If the line integral wasn't over a simply connected curve, and if for example C looked like this, right? If your C was just a not simply connected curve and it was just a path, then there would be no way to write an equivalent region of this integral, right? This curve does not close a region, where in this case it does. It's a simply connected curve if you combine both C1 and C2, and then therefore it would enclose a region that you could use for the right-hand side of Green's theorem. There's another one on here that I forgot to add in the conditions for it to apply. So let me add one over here. So an additional one that I forgot is that the vector field must only have two components. Two components. Right, so Green's theorem is a two-dimensional idea, right? So it's a 2D idea. It takes place in the plane. And you can see in the formula there's only an m and an n component to the vector field, and we're writing the double integrals over a region, so this only can be used if your vector field lies in a 2D plane, and you can write a region in that 2D plane. So it doesn't work for three-dimensional vector fields. Now there is a formula that we're going to get to. It's called Stokes Theorem, which is kind of the three-dimensional equivalent of Green's theorem. It's the more general version of this, but we're going to start out with just Green's theorem, and because it's only restricted to 2D, sometimes it's called Green's theorem in the plane, right? Sometimes it's referred to the full title, which is that. And now here, I have the last condition for it to apply. The vector field should not be conservative. Now, it's really weird to see the word should appear in a condition for application, because it kind of suggests that it's not a requirement, but it's an ideal situation, right? And that's why I have the asterisk at the end, because it's interesting. The vector field should not be conservative. And if you think about what it meant to be integrating over a conservative vector field, it should become obvious why this is a suggestion. Because if you remember, line integrals over conservative vector fields that are connected, right, they always equal 0. Right, so anytime you integrate over a closed loop on a conservative vector field, you know that it will evaluate to be 0. There's 0 circulation done over that integral. So it wouldn't make sense to use Green's theorem if you knew that the vector field was conservative, because if f was conservative and you're integrating over a closed loop, right, then you would just know, without even applying Green's theorem, that integral would evaluate to be 0. So in that case, it's kind of a trivial, it's a trivial case where you wouldn't need to apply Green's theorem, but the reason why the word should is in there and the asterisk is added at the end, because you can apply Green's theorem, but it would also just evaluate to give you 0. It's just more work than necessary. So these are kind of the conditions you should look out for that would indicate this is a good opportunity to use Green's theorem. And now let's go into a couple examples where we can see Green's theorem in action and how it can make evaluating some of these line integrals much easier. So let's look at example 1. We're going to evaluate the following line integral, and I guess we can just check off some of our conditions, at least for the first one. So we must be evaluating a line integral over a vector field. Check. It's a line integral where this is the m, right? The m and the n component of f. Let's see. The path of integration must be simply connected. That's true if I just do a sketch of what C looks like. So let's just sketch C real quick. So C is the triangle bounded by the lines, what is it? X equals 0, which is the y-axis. x plus y equals 1, which would be this line, and y equals 0. Okay, so the path C is this path right here. So here, oops, let me do it in a highlighter. Here is our path of integration C. All right, so this right here. So yes, that does look like it's simply connected. The vector field should not be conservative. I guess that's a good check to do in the very beginning, just because if it does turn out to be conservative, then we don't have to mess with anything. We just can write down 0 and move on. So let's just check to see if it's conservative real quick. And if you remember, the test for conservativeness is dm dy needs to equal dn dx. So let's just check that real quick. Dm dy is 2y, and dn dx is 2x. And so those do not equal each other, so we know for a fact it is not conservative. Okay, so we checked that, and then the one I had to add is the vector field only can have 2 components. So yes, it is a 2-dimensional vector field. So everything checks out for Green's theorem, so let's apply it. So Green's theorem is going to say, instead of having to evaluate the line integral, which in this case, we would have to have 3 different line integrals that we sum together. There would have to be one for each side of this triangle. You could not parameterize this path in one parameterization. We'd have to have 3 distinct ones, and so at least you would have to have the sum of 3 different line integrals using the traditional method. But we can use Green's theorem to say that the circulation is equal to the double integral over R of dn, sometimes I forget the order. It's dn dx minus dm dy dx dy. So it's the double integral over this region. All right, so here's our region where the integrand is that curl term. So let's set this up with some actual numbers. So in this case, it might be helpful if I just write these intersection points real quick. So that's 1, 0. That will be 0, 1. This line is the line, if I solve it in terms of y, it is y equals 1 minus x. Okay, there we go. So we have all the bits on our graph that we might need. And so now I'm going to write the actual double integral. So it's the double integral where our integrand is dn dx minus dm dy. So we know dn dx in this case is 2x minus dm dy is 2y. dy dx. And so now if we're doing the differential in terms of y first, we need to go from y equals 0 to y equals 1 minus x. So 0 to 1 minus x. And then x, to capture that entire region, will go from 0 to 1. And now we can evaluate that out. If we integrate in terms of y and plug in 1 minus x for each of those, let's see, we'll end up getting, if I can do this in my head, negative 3x squared plus 4x minus 1, right, all of that dx. And then differentiating that in terms of x, that becomes negative x cubed plus 2x x squared, just minus 1x from 0 to 1. And then when you plug in everything, you'll get negative 1 plus 2 minus 1 minus just zeros. So that gives us 0. Okay, there you go. So the circulation around this path does evaluate to be 0. Now, it doesn't evaluate to 0 because it's conservative. It's actually not a conservative vector field, but it just happens to also have 0 circulation despite the fact that it's not a conservative vector field. So that's just a little interesting as well. Okay, let's look at example 2. So example 2 is asking to find the work done by this vector field over the curve C, where the curve C is another triangular region in the first quadrant, enclosed by the lines 1, x equals 1, and y equals x cubed in the x-axis. So let's just sketch out what C looks like real quick. So the path of integration is going to be in the first quadrant, and it looks like, let me pick some colors. So the x-axis, so it's bounded below by the x-axis, the line x equals 1, which would be something like this. Here's x equals 1, and the curve y equals x cubed, which I'll draw a little bit over here. Kind of looks like that, and then it comes up like that. Okay, cool. Oh, I see why triangular's in quotes now, because it's not exactly a triangular region, but it's kind of it's triangular-esque in this shape. It just has a little bit of a curved top, where the top of this is the curve y equals x cubed. This intersection would be 1, 1, right? Yes, 1, 1. There we go. So that is our region, and we're going to traverse it like this, right? So we're starting here, and we go up and down. So similar to example 1, this one would also have to be written as the sum of 3 line integrals, but we're not going to do that. We're just going to use Green's theorem to write it as one double integral over this region R. So here's our region. So in this case, M is our 2xy cubed. Here's M, and here's our N. And now we know that work is the same. It's like the interpretation of circulation if F is a force field. So we know we're doing the exact same process. So work, right, is going to be equal to the double integral over R of dn dx minus dm dy over the area differential. And so now we just need to plug everything in. So in this case, it's going to be the double integral over where the integrand is dn dx. So the x partial derivative of n, which in this case would be 8xy squared. So we have 8xy squared minus dm dy, which would be 6xy squared. So 6xy squared. And then we'll have dA. Okay, fantastic. Actually, because we're actually evaluating this one, let me pick an order. We'll just do like dy dx. Okay, so in the y direction, for our bounds on our double integral, in the y direction we're going from the base, which is y equals 0, all the way up until the curve y equals x cubed. So that's pretty easy. So we're going from 0 to x cubed. And in the x direction, we're going from 0 all the way to x equals 1. So it's just from 0 to 1. So you can evaluate this one just like we did in number 1. I will save some time doing the evaluation and let you do that as an exercise on your own. But the answer you're looking for is 2/33. So that is what the work done by moving a particle along this curved path through that vector field. The work is 2/33. Okay, and now let's look at example 3. I believe this is the last one for this section, but it's nice because it also brings up a couple interesting points in this problem as well. So this is another one. It's just asking you to evaluate the line integral of this vector field over a path C, where here is our M, here is our N, the two components of F. And then C, this might be the most complex curve path of integration we've seen so far, but we can sketch it out anyway. So in this case, the path of integration is a circle, and you should remember your notation, your circle equation. What this indicates is it's a circle of radius 2, right? So that's radius equal to 2, and its center is at the point 2, 3, right? That's what the x minus 2, the y minus 3 indicates, is that it's a circle centered at 2, 3 with a radius 2. So that looks something like this. So the path of integration would look something like this, right? You'd come around here. Okay, so let's set up a Green's theorem equivalent integral to find the circulation of this. So in this case, we'd have the circulation is equal to the double integral. I won't write out the full formula this time. I'll skip straight to plugging in these specific numbers. So it's going to be the double integral over R, which R in this case is the circular region. Now, I'm looking at it, and because the region's circular, I'm thinking this might be a good candidate for polar coordinates, but I'm going to evaluate the inside, the integrand like I usually do first. So in this case, dn dx is going to be, let's see, dn dx in this case will just come out to be 2, and dm dy in this case will come out to be 6. All right, so all we're getting is 2 minus 6 dy dx. And here, so here's what I see. And the reason why I always do the integrand first is I can simplify this to be the double integral over R of negative 4 dA. Now look at this trick. So anytime you have constants as your integrand, you can always pull those out and have them right along as coefficients out front. So this is equivalent to saying negative 4 times the double integral over R, and this would be the double integral of 1 now. And if you remember, anytime we do the double integral of 1, the interpretation of this is, this is the area of R. So in this case, what this is now saying is the circulation, this line integral, is really just equal to negative 4 times the area of our region. Because we were able to pull the negative 4 as a leading constant out front, a leading coefficient, and that just left us with the double integral of 1. So in this case, because we know it's just a circle of radius 2, we can just do negative 4 times pi times 2 squared, which in this case will end up giving us negative 16 pi as the answer. So this would have been relatively hard to write as an area double integral because the tricky part really is that this region is not centered at the origin. So it's definitely possible to have done, but because it's not centered at the origin, it would have made it quite a bit trickier. But because we evaluated the integrand first, we're able to see that the integrand was just a constant that we could pull out front, and then just multiply that by this area term, right? Because we know that this portion here will always just give us the area of R. And so we were able to use that and kind of simplify again. But all of this, again, is thanks to the properties of Green's theorem and how it relates line integrals through vector fields over curves that are closed and simply connected to an easier single double integral over an equivalent region made by that curve of integration.